Hello and welcome to 21st lecture of the course on data-enabled tribological engineering, from experiments to predictive model. Topic of this lecture is data collection and pre-processing. Sometimes we say instead of pre-processing, processing. Processing is a overall, whenever we deal with the data, it has to be done with that. Let me start with the initial some topic on the tribology. We say what is the really importance of data in tribology. We have already studied that in tribology we have two surfaces and we use the word tribopair. So this is a 1 and 2 is a friction pair. To avoid wear and friction, or to reduce friction and wear, we require a lubricant. And we get a number of data related to this. But major issue comes environment. Most of the time environment changes from one lab to other lab, one situation to other situation, and that makes more difficulty for us. Reason being, even though speed and load parameters are same, but environment parameters are changing, so results may be somewhat different. However, whatever we can extract from literature, we try to extract. And what is possible? We say this literature data will help us in a quantitative analysis. They will provide knowledge to us, and they can provide some sort of early model to detect the issues. So coming to the quantitative analysis, we say data collection yields a crucial quantitative measurement that includes the friction data, coefficient of friction or coefficient friction force, wear rates, and lubricant effectiveness. We say the lubrication effectiveness can be only compared when we know the friction values and wear rate values properly. So in overall, we can say it helps in a comprehensive assessment of tribological systems. Many times we have a theory, or number of authors have given the theories, but those theories will not match 100%, and or maybe in our situation. So in the situation we need to refine those theories. Sometimes we want to develop a new materials and we do not have any clue about the friction and wear rate. So that's why the data comes from a previous data. Even though we are going out the new material, but lubricant properties may be different, may be same, or maybe the operating speeds may be same, operating temperature may be same. Those need to be accounted. Once we have all those, we can even think about optimizing the machinery or going ahead with the optimization. This will be explained optimization phenomena in the next 2-3 slides. Coming to the knowledge exchange, we say whenever we compare our knowledge with other knowledge, that it helps us to accelerate the research work. We will be able to find out the some sort of a research gaps. Smooth exchange of the knowledge enhances the research activity, that we know very well, and moreover we get a good solution from existing literature also. So it provides a more effective solution to us. Sometimes we say that whatever the existing models are available, and if we are getting a new data, we can combine it. That increases the research productivity and it widens the scope for the applications. Coming to the early detection, here again we require some sort of initial models and online collection of the data, or inline, maybe say offline connection of the data. Those will help to provide what is the really expected behavior and how the component is behaving slightly different manner, and this helps us to come up with a proactive maintenance strategy and try to solve the problems much earlier compared to the costly failures and downtime. So we can really bring economic solution and keeping minimized downtime. So this is overall important to us. We already studied that if we implement tribological knowledge in India itself, it can save roughly 9 to 12 lakh crore per year. So that's a huge amount, and that's why we require this kind of knowledge. How do we go ahead with this? We generally get the signals related to friction and wear, and a lubricant effectiveness can be calculated whether friction is coming down or reduced, wear is reduced or not. We require a number of the sensors. It can be temperature sensor, pressure sensor. Here it can be atmospheric pressure sensor as well as a contact pressure sensor. We require a pH value, particularly lubricant. If it's getting acidic, we require a pH values. We require environmental humidity, or maybe if the water is getting mixed with the oil, then we really require the value of that water content. Every mechanical in the system will vibrate. We will then detail this in the next lecture. We get a number of wear debris, and if we have a wear debris sensor, it will really helps. Now in these days a new thing is coming, image. You take an image and analyze it, and image analysis really provide a lot of information to us. So capturing images and analyzing is coming out to be a very big tool, or we say the sensing unit for us. Many times we calculate the wear volume using the surface roughness or change in the surface roughness. We measure the viscosity, film thickness, hardness, and various parameters. So we really require a various sensors, and this kind of a sensor which can be done or can be utilized, it will be after the what we have already captured, or dig out the information from a existing literature, and after that we are assembling it. If we are trying to make some sort of a test setup, and we are running experiments, and that helps us to go ahead with the proactive maintenance or predictive maintenance. That really helps in a big way, and it may provide a overall good economic benefit, and we can save at least a few percentage of the 1 to 1.5% GNP. Now, whatever we do, we say that this all the data with the temperature, humidity, pressure, pH value, everything is a statistical. We don't get exact one value if we take a different samples. That's why we go ahead with a minimum value, maximum value, standard deviation, mean value. So whatever the tribological parameter or data which we are getting from a sensor, they remain statistical, and we need to quote minimum value, maximum value. Of course, mean will come from that, and standard deviation. So to plot those results, we really require more meaningful variation. Or we say that we should really point out what is the mean value, what is max value, and standard deviation. Now, when we talk about data, we need to think about what are the data sources. We divide mostly in the two big subdivision. We say the primary sources and secondary sources, and this data related to the friction, wear, and lubrication. Otherwise, there are many data. People talk about interviews and the filling the form and all. We are not talking about those things. We are here talking only the friction quantitative data. Qualitative data we are not talking in this case. Let's take a friction, which we have already described in earlier lecture, but again I am trying to repeat here. It says a measurement of the force resisting relative motion between two surfaces. It is very critical to minimize energy loss or go ahead with energy efficiency. We can think about the load cell to utilize to get a friction force data, and sometimes we use a torque sensor. And one of my setup I use a load cell, and one of the seal unit I use a torque sensor, and both can give the good results to us. Coming to the wear, we say that material loss or degradation due to mechanical contact, whatever the material loss is happening from the surface, that need to be counted. Of course, it impacts components lifespan, so that's why then the measurement of the wear is very important. It can be measured in weight loss or volume loss, or maybe the dimensional loss. It depends. Now in this, as I mentioned, that we are talking about surface roughness, so naturally we need to think from dimensional losses, or maybe say increase in a clearance, something like that. Coming to the lubrication, we say that assessment of effectiveness of lubricant comes only by measuring first and second, say how much friction is reduced, how much wear has reduced. And sometimes we have a oil analysis, something like we assess the oil quality, whether after 10 hours or 100 hours or 1000 hours, whether lubricant quality remains same or it has got some sort of other elements. We will describe those things also. Now coming to the secondary data, in this case we already have studied this slide. We studied this in the lecture 20, and then we found that there is a data, or there are number of the units are available or sources are available which are providing the tribological data. Of course, it is not available openly. but when we approach to the authors, they may provide us some information on that. So if we are using this kind of data, or any research publication or any book which are quoting that data, we can utilize those data, and that will be called as secondary data as such in this situation. And coming to the primary data, we need to collect data our own. Either we do the simulation, but I prefer to go ahead with more experimental analysis, because again, if I go ahead with theory and try to define that, again I will have some sort of simplification. So I prefer to collect the secondary data first, come up with some sort of model, and go ahead with some sort of experiments. So instead of doing the too many experiments, I will do a lesser experiment, but will get a lot of knowledge from a existing literature, from a book, work on that, come up with the right model, so that our overall results are in favor to us, or it will be much more robust results. Sometimes people use a word of physical measurement, system measurement, friction coefficient separately, wear lubrication property, surface roughness, and material composition. But again, these are the subjective. We don't want to go ahead with this kind of division. We say, yeah, we can measure the temperature. The thermocouple, or in these days we are saying that infrared scanning camera is a better option, because of the non-contact, from distance we can measure it. Of course, every time we require more calibration. If I don't do calibration, it will not give good results. Pressure, load, humidity, hardness, these are the we can sense, or we can measure it also. Coming to the system level, where the not only the individual but whole system is getting involved, like acoustic signals, vibration, slip measurement, film thickness, where the two surfaces are coming into contact, and we are trying to measure the gap between this, and assuming this is a film thickness. Friction coefficient we already discussed. Even in this stage, wear is also measured in the debris classification. What kind of wear? We can really classify that this is a cutting wear, maybe it is coming because of abrasion. Now it is a plate kind of thing, or a laminar shape. It can be either fatigue or can be adhesive wear. We can classify based on the debris, the shape, and so debris dimension also. To some extent, we'll towards the end of this lecture, I'll show you the few slides on this. We can measure the viscosity, we can measure the pH value. As I say, if the oil is getting more and more acidic, we need to change it, otherwise it will cause a corrosion or rusting of the surface itself. Now moisture, extreme EP properties also can be checked. Particularly, we use a 4-ball tester to find out whether the related lubricant can handle the extreme pressure or extreme load or not. We use a profilometer, but it is a kind of offline, in situ we are not able to do, but here the research is also progressing. The people try to capture the images and try to use that image as a way to predict some sort of a surface roughness. This instrument, like a surface roughness or a SAM, TAM, EDS, all are related to the analytical instrument, and sometimes we use a word to the defined analytical instrument. We say that instrument which can analyze or characterize the composition of the substance can be termed as analytic instruments. Now coming to the data source, or the secondary data source, this is what I am trying to show here. I mentioned also that most of the data are statistical. So if you look at here, the data has been shown. This is a mean value, this is a max value also, and that has been shown here, and then mean value has been plotted. Whenever, then again standard deviation also should come. Similarly, in this case, a coefficient of friction, you are able to see there is a variation here. So this is a necessary to plot, because we don't get any fixed value. Coming to the film thickness, you can see the variation is much more compared to the friction itself. However, in my observation, I found the coefficient of friction varies also significantly. Here in this diagram, it has been shown a running in behavior, that's a stage 1. Then comes on the film formation, that's a stage 2, and last one is that steady state. So that they have been plotted. So we understand. So secondary data are required to understand the system, to come up with some sort of a hypothesis, and once a hypothesis is done, then you validate against experimental setup. Now this is another one where many times we pick up the relation from a literature. Here it is being given that it says that in presence of a high pressure, lubricant density also increases. Earlier we discussed this thing, viscosity increases because of the increase in a pressure. And the viscosity decreases because of the increase in the temperature. Here this relation has been given in terms of the density, and you say the initial density or atmospheric density has been given for the mineral oil something like 0.8 to 0.9. For the synthetic oil has been also been shown here that density changes or atmospheric pressure, what is the density of the this kind of a lubricant, and with increase in the pressure that this should come over here. So it is the same thing which we have already learned for the viscosity, and then particularly that the viscosity increase with the pressure. Similar kind of thing has been given again. Instead of going ahead with a firmly or 100% believe in this relation, I'll take some sort of a judgment, and maybe directly or indirectly I'll try to verify this data. So again, any relation which is available in literature, it will help us to understand the system, but it cannot give 100% results to us. So that's why we say we learn from a secondary data and then use our own experimental setup or our theory to come up with the right results. We also have a secondary data something like a grease lubrication. Now one book says that whenever there is a operating speed more than 2 meter per second, we should not use a grease. Then we studied the Niels handbook and we say that operating speed can go up to 10 meter per second. Now here we are saying instead of that we are talking about the NLJ grade. In everywhere we should use, instead of only speed, we use a dn value. Here the d is also coming the dimension, in here the diameter which is being given in mm, and if it is diameter is not given, we will go ahead with like a gear which will go with a PCD or circle diameter, and rotational speed has been given in RPM. It says very clearly that most of the time which people have given earlier, it was for NLGI 3, then NLGI 2, NLGI 1 and NLGI 0. Of course, we have double zero and triple zero also. Those are also greases. It's not that those greases are not existing. Those are the greases only we talk about something like a thin grease. May require some sort of lubrication system, but not as good as liquid lubricant. So you can see here that this is a 2.5 lakh to 3.5 lakh DN value, NLJ 0 can be utilized. So when we go, we learn from literature. One book, one article may give one information, other article may give another information. We need to extract what is the reason behind that. If the reason is a valid, we should understand and then implement, and that's why we are saying the machine learning algorithms will help us. Reason being, we are extracting information from various sources, and which source will give me the more reliable results I do not know in exactly. So we come up with a justification, tabulate everything, and come up with finally that how do we go ahead. Again, machine learning is a continuous improvement. It is not that somebody has written a book or grease selection should be done at the time up to the 10 meter per second. It's possible I can go ahead with the 15 meter per second, but what variation is required? How do I go ahead? That's where the understanding or innovative thinking is required. Now coming to the primary data source, we say generally we have an environmental sensor like a temperature, pressure, environmental things can be captured. We have a laboratory, we do oil analysis. In oil analysis again we have two categories. We can measure the viscosity and FTIR, of course, and this is as per what my laboratory has, but I'm not saying that this is restricted only this, it may be many more options also. Coming to the characterization, we use SCM, we use a TAM, we use EDS, and we use a surface profilometry, and many more are possible. AFM I don't use, but AFM is also possible and we can utilize it. We use a tribometer to find out the friction and coefficient of wear, or with the wear analysis, or we say the wear loss also. Coming to the this is what we say mostly is offline analysis. I'm using the word offline analysis. I can't do experiment inline or in situ. Here we can use a measurement in situ, particularly for tribometer, but again the tribometers are only simplified tribo pair which we use. We don't use actual experiments, and for actual experiment, actual in situ measurement, we use a number of sensor. Like I use oil analysis using the sensor. We count the particles, we use a sensor. We have a quality index sensor. So these are the sensor. We have a load cell, we have accelerometers. So they can really give a in situ information. What is the meaning of in situ? You say measurements are taken directly from operating machines or system. Again, I'm not simplifying the way it has been done in tribometer. In tribometer, we simplify the tribo pair so that I can conduct more number of experiments in a lesser time and lesser noise. Reason being, tribo pairs are well controlled condition. In actual system, actual machinery, we don't get that kind of complete hold on that, and there may be number of gases also. Let's take example of the gearbox. Gearbox has a C. Gearbox has the gears. Maybe if it is a single stage, then only two gears. But if it is a planetary or a multi-stage, then more number of gears. Then every gear pair will have some sort of supporting elements. So maybe the rolling element bearing, maybe some sort of seal, maybe with some sort of a tension, so that it can be located properly. So overall gearbox may have a number of components. So when we do in situ measurement of number of components together, then we will get a lot of interference of components. And how to avoid those interference? That is where we really require this kind of a lecture. Now, what we are using the word, there is a diverse interaction, and basically in tribo cases, the different kind of interaction happen with surfaces. One of the major thing comes to heat transfer. So, if somebody has given a one tribo pair or maybe say one gear pair, and he has given the results for the some sort of module for the pitch circle diameter for the lubricant, but if he has not defined or she has not defined completely how the heat transfer happens, we will be getting different kind of wear rate, we will be getting different kind of friction coefficients. So that's very important to understand. Second thing comes apparent area versus the actual contact area. I have found that most of the literature, when we try to review, they don't define the surface roughness, and surface roughness maybe directly doesn't come into the picture, but it is really affecting the results. Now, how do we define the apparent area of contact? We say simple: a normal load divided by yield pressure of a softer material. And that's why reason many people define the pressure and define the load, yield limit and the normal load, and they feel that they are sufficient. Now, we need to really define a surface roughness. The actual area of contact is basically sub area in physical asperative contact. Now, we know very well, if load increases, number of asperities which will come in a contact will increase. But initial running in period time, surface really affects a lot, and quite possible when the load changes, operating speed changes, temperature changes, again asperities will come into picture. So, it is always advisable to define what is the surface roughness, and not only Ra value, we should go ahead with the Rq value, we should go ahead with the kurtosis and skewness. All four parameters are very important. If we don't define, naturally we are not giving, we are not disclosing all the conditions. So, in my view, in the future, particularly in machine learning algorithms, we really require this kind of values. Earlier, people were not defining because the modeling itself was very difficult, and this kind of additional data will increase the complexity. So, initially they thought only for the simplification, but we know very well that cost which can be saved because of the tribology or by implementing appropriate tribology is a huge. So, we should go in a right direction, and we should define the surface roughness parameter appropriately. One more thing comes of foreign particles. Now, in this case, particles can be dust, it can be wear debris particles, and how the wear debris particle have been removed from a surface. If that is also defined, then it makes much more sense. So, if it is not defined, again I'll go ahead, I'll explore the literature completely, I'll try to figure out what is really available to me. We will learn those from literature, come up with some hypothesis, come up with some sort of model, and implement, do some sort of experiment in the lab, so that we get overall robust results and we get a confirmation on that. Now, we can define maybe one slide I have kept only to define what is the really real time, what is the offline data, because in previous slide I say offline data, offline measurement technique and in situ measurement. So, what is a real time? We say real time data collection is basically data collected and processed immediately during a tribological interaction. That's the in situ, immediately it's been done. It has a number of advantages. We say advantage is immediate insight we get into the friction and wear train. and if we know that something is going wrong, we can immediately correct it. And then we say this kind of a feedback system can be given. Now this kind of feedback system is very much required in robotics, a very much required in manufacturing process, and very much required in hydraulic system. If you don't provide feedback, quite possible whole system may fail or become inefficient. So that's why we use in surface loss. If you, that's what I mentioned, that now the future is that we should be able to predict the surface in situ, how the surface is changing with the time, so that overall results are in a favor to us. If we are able to do that, then efficiency and damage efficiency can be improved, the damage can be reduced to significant level. I shown in situ measurement of the coefficient of friction, which we did on the 4-ball tribometer. You can see here initially coefficient of friction is roughly 0.1, and with the time it has increased to the 0.13. So this is very important to see how the changes are happening. Now, in this case, I have given a couple of examples that we do wear measurement using the wear debris by counting the number of debris and size distribution, and we also do the friction measurement directly in engine components, because we need to really come up with a right result, and which the interface is really giving high coefficient of friction. That's more important. We also do oil monitoring online. We have a sensors, so we do it. Now there are a couple of system where it is a very essential to go ahead with in situ measurement. We say any equipment which is handling the slurry, if it is not a costly, then there is no need. But if it is a costly and it is a reliability requirement on the higher side, I'll go with in situ measurement. Like even machine manufacturing or cutting tool or gearbox, particularly gearbox, which I'm not able to reach immediately. It is like a wind turbine gearbox, which is very at a very high height. A gas turbine, maybe temperature is very high, we cannot reach directly. Gas compressor, hydraulic systems. So these are the units where we really essentially require real-time measurement. Coming to the, of course, these measurements are required also along with the diagnosis capabilities. So we keep getting a data, and then we should have algorithm to diagnose what is really happening. Coming to the offline data, this is also very important. It's not that we get only inline and then we'll be fine. Offline data is also important. We see data collected and analyzed after tribological event which has already passed or occurred. What are the advantages? We get overall analysis. So here overall analysis is important. Like let's take an example, give an example. When we are using the wear debris analysis, we get some data, some value, because whatever the sensor is able to record, that value comes to us. But sometimes wear debris generation is much more higher compared to the sensor, so we get a more wear loss as a result. When we do offline analysis, we get a more number of the debris particle, and that is a very important to understand. And in when we do this, we also are able to keep a record, and then it will be useful for the maintenance purpose or maybe for historical purposes, or in the short I can say it can be used for the long term analysis. So when we are recording, it's very important. Now here we use ferrography kind of analysis, wear debris analysis, where we can use a microscopy, spectroscopy, elemental analysis also. So ferrography is the one where we can separate the particles, maybe in different range we try to figure out. But subsequent to that, we can use microscopy to understand what is really the shape of the particle, what is the size of the particle. We can think about spectroscopy to figure out the Raman spectroscopy itself. Coming to the element analysis, we want to know what is oxide level on the surface, what kind of oxide or what kind of molecules are getting transferred, or what kind of lubricant layer is remaining on wear debris. Similarly, surface profilometer, we generally go ahead with the surface roughness, texture and topography. And material characterization, as I mentioned earlier, that we really required properties. So here in this case particularly we take hardness, because we know the hardness and the wear rates are related. We do the tensile testing also. We go ahead with the metallography to understand the material response to friction and wear. So sometimes these are also required before engaging, before starting experiment. This is important. I'm showing one of the image which we collected from a 4-ball tribometer experiments. Here the ball has roughened completely. You are able to see that roughness on this surface, and it is very what we say, the very rough surface after the testing, and thus we do not get a immediate response or in situ response. In situ response we are able to get a coefficient of friction, but why the coefficient of friction is behaving like that, that can come when we do a post analysis or after completion of experiment, that analysis. There are several benefits of collecting data. It provides insight into system behavior. It allows optimization process to be started, and it really gives a verification of the theoretical model. It also ensures a quality control. It reduces the cost. It is one of the important thing is that it really consider the environmental and safety. It is very important, and it also provide an opportunity for the innovation. Now, inside into the system behavior, reason being that tribology is very complex phenomenon, and then we are not able to understand all the interactions immediately and how they will behave. Once we start collecting the friction wear data or lubrication data, other temperature data, or even humidity data, then we can really think about how the interactions are behaving, and we can monitor the interaction in real time. And then also gives the different kind of variables, like I'm initially assuming 10 variables will affect the overall system behavior, but later we realize the 5 variables are much more sensitive compared to remaining 5. So that also can comes, that means initially whatever we hypothesize, that also can correct it because we understand the system in better manner. Coming to optimization, we say that it really identifies where the friction is really increasing, where the friction is decreasing, and whatever lubrication we are doing, how it is really working with the system. It minimizes the wear rate, or the increasing the wear rate, or it's not affecting the wear rate. So it really allows us to optimize the situation and really do a design of the system so that we get optimum results. Coming to the theoretical models, we say that mostly the theoretical model which have been utilizing, they do not have a right results, and often they come up with a one constant or two constant or three constant. So then becomes a empirical into the, it doesn't have a complete science, and where because we require some sort of corrections, so correction factor comes, and then correction factors when we are adding without any science, that it is bringing some sort of empirical nature to the system model. For that purpose, what we required, we required experiment this data to understand the what is really happening in individual situation. So understanding mechanism in individual situation is important to us. In quality, we say that we don't want any failure, and as I mentioned earlier case, that there's a difference between fault and failure. We are more concentrating on the faults, not a failure. And if we are able to find the faults and immediately correct it, then the system reliability will be enhanced, performance will be also enhanced. So in real tribological sense, we really require in situ monitoring, get the data collection, and then immediately react on that so that overall results come in a favor to us. However, if this kind of cost is on a higher side compared to the tribopair cost, naturally we will not be able to do. So there is a need to go ahead with innovation. So wherever the more sensors are getting costlier, system responses which we are getting from sensors is getting costlier, we need to really do a innovation. We need to bring some sort of cost effective sensor, cost effective solution, cost effective strategies in the situation. So if we are able to do, we will be able to save the cost. And as mentioned in one of the earlier lecture, we want to really refabricate so that system or can be used, or component can be used, or surface can be reused. If that's possible, then it will naturally will save the environment. Will go for the more sustainability. Even if the failures are not happening, it is going to really help us a lot. And now in this case, one of the important thing is coming as sensors, which has a huge market. If you look at compound annual growth rate is coming around 18%, which is a huge. And there is a new term in these days being coined, is a digital twin. Can we really replicate whatever is happening in the real system in a simulation system? If that's possible, it will really help in tribology in a big way. Now that's why I'm keeping two slides on a digital twin. We say when we think about a digital twin, it enhances the tribological knowledge. It's unfortunate really that awareness of tribological potential to reduce CO2 emission is not known to many people. And then it also enhances sustainability. That also information is not available to many people. Now you talk about power plant, you talk about automobile, you talk about the turbine and the wind turbine, you talk about gearbox failure. Everywhere energy efficiency, sustainability comes from a friction and wear point of view. That means tribology plays important role. Let's take one example of the wind turbine. We say it's now a growing source of electricity because we are talking about the renewable energy, either solar or wind, and wind and solar are playing major role in this case. Now they encounter downtime and efficiency issue. What are the reason? Major reason is the gearbox. Now gearbox is they are mentioning around 76% of the gearbox. All the failures are because of the gearbox failure. Again, gearbox failure is because of the bearing failure. Even though it is a gearbox, gears are not failing, but bearings are failing first. So you need to know about those things. Now why it is happening? Because there is a fluctuating wind and the grid load. The load is changing continuously. That means there is a dynamic condition or dynamic situation. Predicting the dynamic condition is in these days it may not be easy. So we really require the in situ sensors, and we really require in situ actions. How do we go ahead? So predicting dynamic condition and modeling is important, so that overall operational expenses can be reduced and maintenance expenses can be reduced. So that's why we require the data sensing. We require actuation system which provide the guarantees to us that tribological challenges which have been faced by the wind turbine can be solved easily, and wind turbine health will be in a good condition. However, as I say that many times we don't have all the sensor, and that's a future. So we say that cost effective measurements, we really require a research on that. We require a monitoring. If it is really wireless monitoring can be done in a much more effective manner, or we can provide some sort of digital twin system. What is happening on the top, maybe say the height, and the same thing is projected in the lab, and that too not only sensing unit but replica of the system which we are operating, then it will be providing much more optimum results to us. So that's the future. So that's why we say it is develops a reliable solution and accurate prognostic approaches. Now we are talking about something like a cyber physical system, as I say in tribology, because it's the most complex system, and then we want to understand really at the nano level what's happening, and that's what is the best. Go ahead with cyber physical system. That's why the cyber physical system in tribology, we say modeling a physical system in a digital environment to simulate the real machine behavior. So this is what we are saying, that what is a type of cyber physical system is a modeling of physical system in a digital environment to simulate the real machine behavior. Not only this, and when we have a physical system, it has a number of sensors, so we are able to see each and every sensor properly. We are able to model and then do a continuous monitoring. We say continuous monitoring, continuous control, and optimization of equipment performance is possible using this one. This also helps to enhance the service management, increases the product life, and in this case also we say that whatever the software or whatever the model which we had developed earlier, that also keep getting updated because we are getting all the data. So initially we designed some system, we made a model, and then we made a physical system. Now physical system is getting engaged into the real situation. What is happening into the physical system, that also is transferring the information keeps coming to the software, or this is a digital entity. And now if the surface is getting roughened, my digital unit or virtual unit also should get roughened. If there is a wear loss of the physical system, wear loss should also be reflected in the virtual system. Then it will be called a digital unit, or maybe like a mirror. We are using a physical system, there is a mirror, and other side there is a virtual unit. So whatever the physical system, real physical system is doing, virtual unit do the same thing. That's why it is known as a digital twin. We say essential knowledge includes in this case data acquisition, analysis, knowledge management for estimating. Then one of the more important thing is that what is the remaining useful life. So if the remaining useful life is a 5 hours or 50 hours or 500 hours, that can be done. So this is very important to us. Let me continue is, you say it is really helping to enhance the tribological knowledge. Now what are the challenges? I find that there are some challenges, particularly when we do work. Here we are estimating smooth surface is required, but how much smooth? That can be when we go with a digital unit or digital twin, we say it will highlight the need of sufficiently smooth surface finish for effective lubrication. Here we studied earlier that nanoparticles are helpful, but nanoparticle size should also be comparable, or maybe say there should be some proportional to the surface roughness. If surface roughness is increasing significantly, the nanoparticle size also should come down. It will not cause a more, otherwise will not be effective. That can happen when we talk about the simulation, or we try to make a digital twin. And then we say it addresses whatever the, in case there is some sort of roughening problem is happening, how the lubricants need to be changed, that should be given to us, information should come to us immediately. And then in otherwise what will happen, those unit will be subjected to adhesion or seizure. Sometime if there is an abrasive particle, how to remove it, how to filter it. Maybe once in a while we need to filter complete unit, or we need to change a lubricant. That will really save a lot. So this is a digital unit is very important, or digital twin is very important. Similarly, we need to deal with the challenges in wear testing. So what are the major thing is that many times we do a four-fold test and then we assume there is a planar surface and surface of is not roughened. So we calculate wear volume, loss of the wear by assumption, by formula, and reality it is not happening. So that is where we need to say that that is a limitation of existing units, and that's why we digital twin can solve those kind of things. And we really required shape assessment also. Maybe we'll show in the next lecture one of the shape of the football. You can see very rough surface coming out, and because the shape is changing, we cannot really estimate wear volume appropriately. So classical traditional tribology, what we have been doing, we have been assuming a lot, while if we are able to implement digital twin, we will not assume, because there the matching has to come. Now my virtual unit should show the same performance as the physical unit is showing. If there is a mismatch, naturally there is a modeling issues and we need to model it. Of course, in a one day model cannot come to the final level, but with the time it should be happening that manner. So that's why we say digital union is very important for us. We discussed about wear loss earlier, adhesion and fracture, abrasion and fracture, fatigue and fracture, and surface alteration also. Now here if it is really adhesion is happening, digital twin should be able to show us. Abrasion is happening, digital unit twin should be able to show us. Fatigue, again it should be shown. Again, it really required all the sensors, required really good models. Otherwise results will not be useful to us. Now there will be direct or indirect measurement. We say in this case particularly adhesion, we know adhesive force is when we need to break the junction, there will be shear stresses, and of course there will be tension also. So are we able to simulate those situations? If there is a crack, are we able to simulate the crack propagation in a digital twin? If it is, then it is good. If it is not, then we need to think how to model the system properly. Coming to the abrasion, we know that one surface will be hard, one surface will be soft, and it will cause a soft surface with deformation will occur. There will be some sort of shear stresses, and then whenever shear stress surpass a material, naturally the material will be getting separated from a surface. So that's why we say it will cause a leading to the crack formation, propagation, fracture, and material detachment. So this need to be really simulated properly, and it is possible only when we have a data and we have a appropriate data analytics and machine learning algorithm. That's why this has been highlighted in this lecture. One more thing comes a tribochemical wear. We say whenever there is a chemistry comes or tribochemical reaction happens, it will change the surface. So here the surface should be captured and how the changes are happening. Now surface from a ductile surface it is getting brittle surface, and we are again there is a mechanical action, and that is removing this debris that need to be captured. So overall this will be helpful if we have a sensors unit, we have a data collection, we have a data processing, and we have good models. It will really help, and finally it will be landing to the digital twin, which is the future of the every type of system. Now, another one comes failure analysis. We have been utilizing the failure mode and effect analysis. If we go ahead with that kind of a system architecture method with the systems using a complete sensor unit, and we do a continuous monitoring using the sensors, and then processing sensors in a proper way, so that we are getting overall good results. So overall data collection, data analysis, data processing and interpretation is very much required, and if we are able to learn all those, surely we are moving to the cyber physical system, we are moving to the digital twin that will be really helping us. So detection of the cracks, material transfer. Now we know very well that even the 2D material, particularly 2D solid material, they transfer layer on a other surface. So they will cause a wear out, or maybe the soft metal they will transfer and then there will be coming out from a surface. Now it will getting some sort of a debris. So this is important to understand for us, and this wherever this happens and we are able to quantify the damage. One more mechanism in these days we talk about the self-healing mechanism, or if the lubricant have a self-healing mechanism, that will really help, and that really required in situ data. And if we are able to process data, we are able to see whether self-healing is happening or not, then only the more innovation or newer material generation will come. It will give indirect measurement, it will give indirect direction, but it will not be able to give a right results. Now in the situation we need to think about how to reduce if we are not able to go ahead with self healing, or maybe units are not been done, or maybe solid lubricants are not sufficient. In that situation also, if we are going with a digital twin, it will allow us to think about reducing the load, so that overall lifespan of the component of physical system increases. Now if there is a crack which is getting propagated because of the increase in the load, if I reduce, naturally quite possible the crack may not grow, and the life of the physical system can be enhanced. That's what we are saying. If we are able to really monitor everything in situ, it will really help us to and it will give a better knowledge about the tribology. It will help us to go ahead with the better results. Now, as I mentioned, in every case, we were prefer to go ahead with experimentation as a primary data source. And here I am talking about the only wear measurement. Subsequent, the next slide, maybe we will be talking about the friction, then lubrication. Now, here wear measurement, we do a direct measurement. We can measure the wet loss. We already have covered something like wear of the pin, wear of the ball. We have already done it, and we measure the dimension. It can be length, it can be width, it can be depth, and to figure out what is the variation, we also go ahead with the surface profilometry, and this is all already been done. Now coming to the indirect method, we analyze the wear particles, and then use appropriate filters to come up with the right solution. We also have a spectroscopy. In this case, X-ray spectroscopy, or FTI, or as I say, Fourier transfer infrared spectroscopy, can be used for this kind of analysis. Volumetric, of course, here we try to figure out first the dimension and then use a formula, so it is indirect method. So we are saying here direct, we get direct results in terms of the wear loss. Here we have to interpret based on the experiments, or maybe say whatever the equipment we are using, and then whatever the calibration constant they have used, or calibration method they have used, or whatever the physics they have used, that need to be understood and interpret the results in the manner. I'm just showing a couple of examples here. This is a wear scar 4-ball tester, and earlier what I was mentioning here, we are assuming this circle is a planar circle. In reality, it doesn't happen. Now coming to the wear debris analysis, we have a single stage gear, and then we have oil samples, and then we use a ferrography where the oil sample is released, and because of the ferrography, iron particles will get deposited based on the size. Here there is a permanent magnet, And subsequent to that, wear debris is analyzed, whether it's a cutting wear, it's a fatigue wear, it is a adhesive wear. That kind of analysis can be done, and this is easiest one. You measure first what is the mass of the block, and after doing experiment what is the weight of the block, and by subtracting this we will come up to that what kind of loss in the block has happened. So wear measurement using weight balance, wear measurement using this dimension, wear measurement using the particle calculation or particle volume calculation. We can figure out using this kind of relation. We already have derived in earlier lecture 5th. We say wear measurement technique, and we found that if you have a dimension, you can find out the wear volume directly. And in this case particularly, we are showing some sort of we measure after every 40 hours, but it can be anything. It can be 10 hours, it can be 20 hours. Every lab has a different way to find out the results, so that can be any data. Now here we are trying to give in situ data. Earlier I was using the after post analysis. In this case particularly, we use a metallic wear debris sensor. We have a oil sensor suit, and then we try to figure out what particle, particularly ferrous particle, which has a range from 40 to 400 micron. We assume that lesser than 40 micron, because our sensor is not capable to measure it. Our new sensor are they are not, we are able to measure the 20 micron, but I don't have that in our lab. Of course, the sensor model has been also mentioned, and what is the principle of the sensor? They go ahead with the magnetic field calculation. If enhancement of magnetic field, what will be the where particles? Of course, it is again need to be calibrated again and again. It is not the once you fix and then you will always get a correct reading. It has to be calibrated again. And now I'm showing here some sort of data. Particularly here you can see number of particles which are getting generated, that has been recorded. Running in time, there are some sort of fluctuation. Normal where it is more or less constant. After 100 hours we realize that the wear debris is increasing here. While coming to the severe wear, we find a very different kind of responses. So this gives directly the gear is supposed to are going to fail. Now this another one size distribution. We find a particle from 40 to 60 micron. This is coming something like a 44.64%. Then particle 60 to 100 micron, we find a 46.5%, and particle more than 100 micron is a very less percentage. Now here we have given all the data after 6 hours, after 50 hours, after 100 hours, after 150 hours, and we operated before complete gear failed the 198 hours. Everywhere you can see here the number of particles, particularly more than 60 to 100, that is happening in 198 hours. And then even the 100 particle size is 4000 particles, they are coming the more than 100 micron size after 198 hours. So initial when we have initial where we are able to see this 51,000 particle which have come during initial stage itself, which is the size is lesser than 40 more than 40 micron, but size in here it has been almost 50,000 particles we are getting after 6 hours itself. Then after then as the duration passes, after 6 hours, then we calculate after 50 hours, we find this particle instead of 51,000 it has dropped down to the 7,000, then again drop down to 6,000, then it may increase to some extent with the 12,000 or for the one for the 150 hours and 198 hours. Coming to the more than 60 micron, we are again able to see initially that the particle size is 13,000, then it drops to the 3,700, 3,500, then after 150 hours it increases, and 2 hours and number of particles are increasing significantly. So by measuring this data we are able to get some sort of a response, how the gear is going to fail and what kind of responses it is giving. Now coming to the friction, we see that it is really required for the efficient overall design or tribo design. We need to calculate, and then we need to really think about how to reduce the friction, improve the efficiency. And then reason being, we already studied that because of the friction losses we have a huge GDP losses, and then we really require to measure it. Can be indirect, it can be direct measurement. Coming to the direct measurement, we use, as I say, the load cell, we use torque sensors, and then in tribo testing, we can do a direct measurement. So we have done in our one of the 4-ball tester, we use a 9 oil samples, and you can see the coefficient of friction, and you can see here the variation is there, is nowhere it is a constant value, it is continuously fluctuating. Now suddenly in between there is a fluctuation coming, the value is increasing, quite possible that the wear debris comes into picture, and that gives a random results. So it can be outliers also, it can be removed. So when we go hard with the post processing, that time it is really required to remove this kind of data, come up with the right results. And coming to the indirect measurement, we can say the temperature rise is one of the indirect measurement. If I'm able to find out the temperature at the interface, I can say temperature may be increasing because of increase in the friction, or temperature decreasing because of reduction in the friction. There's a possible. And then sometimes people say that there is a relation between friction and wear. If I find the more wear, then I say friction increasing. On the lesser wear, friction is decreasing. But these are the different things, and different sensor, they have a different kind of calibration. And sometimes we use a power loss from a directly motor, we find out the what is the voltage, what is the amperage, and then this friction losses can be used indirect measurement by measuring the power losses. It also is very clearly that during initial stage of the friction, we studied earlier the top surface is like a 5 to 6 layers. It's not only one layer. Now here the response has been coming that why the coefficient of friction is varying here. We say it is a reason being the surface screening that experience initial thermal, mechanical and chemical consequences. When initially that this is thermal experience is there, or thermal damage, mechanical damage, chemical damage possible, but subsequently when the damage is reducing, subsequently the damage is increasing, that will depend on the systems. So that's why the running in wear mostly we avoid. We say whatever you calculate you can remove that, don't include in your friction experiment, or we say don't account even the wear experiment. So that's why in one of the lecture I mentioned very clearly, many times people perform experiment of 50 hours, and then after 50 hours they say okay, what is the effective wear constant or coefficient, but we do not know in 50 hours whether 35 hours was a running in time or 40 hours was running in time, or only 1 minute was a running in time. If it is only 1 minute or compared to the 50 hours, naturally we can neglect, there's no issue. But if a 35 hours running in time and compared to the 50 hours, that is substantial. That means whatever the wear constant they have quoting in their research publication in a book, that is now used. It is useless, and we should not believe in that. And another thing is say the machine learning to identify data pattern, because we have learned that machine learning can do some sort of a sub classification. It can really classify and find data on the pattern or 10 data pattern, and then really recognize, understand the pattern, effectively predict the coefficient of friction under various operating conditions. So this is a hypothesis. We are thinking that coefficient of friction can be predicted. However, in existing literature, it is very clear the coefficient of friction cannot be predicted so well. Of course, people have a given number of theory, number of model, but again there is no consistent results. In one of the famous book, Ludema's book, he has given a 2000 relation related to wear, and he says that even the wear prediction is not easy. There are 2000 relation available. Which relation should be believed? So this is important to understand that already there is a gap, tribology gap, and we need to bring machine learning to bridge that gap, so that overall results go in a much favorable, and whatever estimated the cost saving, that should be achieved in that case. Now, coming to the third characterization, we do some sort of characterization. We use analytical equipment. Here, I'm just showing that we have a purchase two particles nano label, MOS2 particle and HPN particle, and then we are trying to figure out what is the chemical composition of that. So we use the EDS to analyze the purity of the MOS2 and HPN, and EDS is a good solution for that. Reason being, the EDS use a high energy electron, so that the material atomic level interaction happens, and in this case particularly the material's inner shell electron ionize, and then they emit X-ray, and if human is able to capture the X-ray, analyze, because that X-ray will be unique for each material, so that will give a response to us, and that has been shown here. In the case of MOS2, we are getting those two peaks. So sulfur is something like a 79.7% atomic weight, and molybdenum is around 20.3. While coming to the weight percentage is a 56.75. So this is what has been mentioned, shown that yeah, this is the purity level is a good. Coming to the HPN, again here N and B, and we are able to see that B also is around 50% atomic weight, and is a 50% atomic weight. Coming to molecular weight, here it is coming 43.8% and 56.2%, and this is a x-axis is a electron volt energy, and every material has a different kind of results. Here we are able to see that here is a much lesser value compared to the this value. Now we have other analytical instrument, Raman spectroscopy, to find out the purity level of nanoparticles. So we are using a Raman spectroscopy also to find out what is a graphene, RGO, MOS2 and HPN. However, in this was taught in earlier lecture also. What in Raman, in fact, we do inelastic scattering measurement. So inelastic scattering of monochromatic light, and monochromatic light which we use in particularly is a 532 nanometer. In this case, we, because of the inelastic scattering, there will be some sort of frequency shift, and wavelength measurement happens, and then is being plotted, and then you can see here in this case the graphene, we are getting D bands and G bands, RGO also D bands and G bands, MOS2 we get a two modes, E and AG, while HBN we get a E2G mode also. So MOS2 particularly when we magnify or increase the size, we are able to see that they are getting two modes. E1 2G mode comes around 382, and then A1G mode comes around 405, and this is coming because of the difference, because of the number of layers, or we find some of the agglomeration happens, and that's why this kind of difference is coming. Coming to the graphene, we already seen that the G and 2D, and the G band occurs something like a 1586, and then we say that basically purity level, purity level is basically exhibited whether the G bands are strong or not, and this ratio has to be greater than 2. If the G by 2D is greater than 2, then its purity level is on a higher side, and basically what we say the G band is showing a stretching of the vibration of the sp2 carbon-carbon bond, which is in a hexagonal lattice, and the band occurs something like a 1350 to 1360, and 2D comes around 2800 to 2700, and this is basically sensitive to the number of graphene layers. So we can find out what is the thickness of the graphene layer, but again we need to confirm using the TEM, which we did in earlier lecture. We have presented that number of graphene layer which are very easily available or seen using the TEM. Now here the reduced graphene shows a better say the purity level compared to the graphene as such. Coming to the HPN, HPN shows the highest purity level. We say it is centered around 1367, and then it again we say that Raman spectroscopy, we go ahead the vibration mode, and then we are using monochromatic light, laser monochromatic light, and then we are trying to figure out what is the inelastic scatter, and based on that we are calculating. So this says here in this case absence of other significant peak in HPN is really indicating that there is a high purity level, particularly for HPN. Now, and similarly Raman spectroscopy, we have other IR, that's Fourier transfer, FTIR, we use oil case. This figure also I have shown earlier, that show the two peaks here, and then the one peak, this is related to water and oxidation, and then this is being compared with a available table. He says very clearly where the wave number is 723, which we are getting here, this is 723. It is causing some sort of a CH banding oxidation. So this is comparison to that. Coming to second one is 879, 879 and 816 again is a CH banding or maybe presence of the glycol. Here 1720 we are able to see 1720 is also oxidation, 732 is also oxidation product, and 31410 is the water. So this is a used oil comparison, and our used oil says very clearly, yes, we there's a lubricant which has been utilized for the after doing experiment for analysis, has a oxide formation, it has a moisture ingress, and it's not really good, and maybe we can change the oil, this oil also. Now coming to the final one or two slide, we say that whenever we are trying to diagnose any bearing fault or any fault, we should have some sort of setup. Here we are showing some sort of unit where the motor speed can be changed using a VFD, and there is some sort of a bearing which is the test bearing over here, and then we try to figure out what is really happening, and we get a vibration signal, and that vibration signal at the 32 hertz operating speed, or shaft operating speed is 32 hertz, and 12 second the time you can see here, the time 12-second data have been captured. Of course there are many datas, and then you are able to see this is acceleration data. Here the maximum value comes around zero. 0.6, while in this case acceleration value goes up to the 1.5, and this is what we are saying, this is a bearing is a faulty and this bearing is a healthy, and this is very important. Now time series, we are able to see the magnitude of acceleration, it's increasing, but that gives a lot of we say that it may happen because of some reason. What is that reason? We don't know. Bearing is getting faulty, that's fine. Now here that we need to really think what are the defect frequency of the rolling elements. We will be exploring little bit more in the next lecture, but I'm just trying to give you some overview. If we do a FFT of the time series whatever has been given, then we can figure out what will be the faulty frequencies and why the faults occur. Otherwise they will not be easy. So in this case experiments, we first do we have a setup, this setup is available in a lab. We first go ahead with the healthy bearing, then we go ahead with the faulty bearing, and we capture the signals. And if for students we say that you can see that what is the frequency analysis and what is the time analysis, time frequency, and this is the time has been shown and frequency I'll be showing after a few slides. We use this kind of theory also. We say the rolling element bearing which have been utilized, it has a number of components. Now if you go with the frequency, I can get a ball pulse frequency outer ring, a ball pulse frequency inner ring, ball pulse frequency, or we get a related to cage also. So these are the frequency response. So if I use a frequency signals, then I may get some sort of response. So if it is coming up related to the the BPFO, then I will say it is a outer ring is getting a fault. If it is coming corresponding to BPFI, then I say inner ring is getting fault. If it is getting FTF, then I say the cage is getting fault. So this is a very important. We teach theory and then we say yeah you go ahead. I've many times we don't have all the details because seals are the closed. Then we will use a rough sort of the things, number of balls, what is operating speed. Then in this case, a previous case I showed a 32 hertz is the operating speed of the shaft. Now number of balls, it is the number of balls, mostly it's 8 to 10, and then if you multiply this one is a roughly I may say that heuristically model available, and compare the results. Now before going ahead with that, we know that there are number of noise parameters. We may have a wrong sensors or maybe say inaccuracy sensor, that's why we require every time calibration. We do have a temperature variation, humidity variation, pressure variation. There is a possibility on the machine which we are operating, sometime it is operating alone and sometime 10 other operation machines are also operating. So there is a possibility of the mechanical vibrations from other systems are getting transferred to this system, and there is a possibility of multi-sensor interference also. So noise level is also possible. How do we do noise? We will be learning in next lecture, and however we say that we really essentially require to remove the noise. That's why we require a data cleaning, and moreover many times we say how much data, because each second we are transferring maybe thousand data, and the many data will come. What do we do with that data? So we need to really think about the function which are appropriate to really come up with the right results. So that's why we say we collect the data, then we do cleaning the data, and then we transfer the data. Like in FT, in this case, we say that from time series or time sequence data which we are getting, we will transfer to the Fourier transform, and then we get a better results. And then after that, if we go ahead with some sort of filtration, we require a high frequency filtration, low frequency filtration, and then data can be reduced, which we require a more meaningful values. So first thing comes, is there any standard available for data cleaning? Unfortunately, we don't find much standard available. We don't find any ASTM standard, ISO standard which can help us to clean the data. So next lecture I'll also tell you how do we go ahead with the data cleaning and get the better results. Now coming to the data transformation from a previous signal. Now here you can see we perform experiments on healthy, we perform experiment on the faulty, and we are transferring data from time domain to the frequency domain. This is important. Now in this case particularly, you can see here when we are going with this doesn't make much sense as to us, but this makes a lot of sense. Now this is a 32 hertz first harmonic shuffle, and this is a multiple of the harmonic, that will be 2 into 32. Right? So this is what we are getting signal. Now here, even though it is a healthy bearing, but I am getting response, the bearing which was a healthy, it has been assembled in a manner, there is a misalignment, and this gives a misalignment effect to us. That means bearing which should show a natural frequency at the 32 hertz, but it's showing also frequency with a high amplitude at a 64 hertz, which is not correct. And of course there are another one also, on high harmonics also we are getting almost a 4 times. That means misalignment is a dominating feature. Whenever we do this, we need to correct it. Now question comes, if somebody has a tabulated in a research publication on a book, oh this is a healthy bearing and we should get a response like that, then we say no, this is better than that. We understand, we should have a domain knowledge how the results should be analyzed. Coming to the faulty bearing, you can see here response, that's 32 hertz. Now here the magnitude is not that much as we were getting, that means misalignment is there but not that much. So this is 64 hertz. Now here we are also getting third, and here this we are getting very high value compared to this. So that's why the whatever the fault which was introduced, maybe crack which was introduced, is really giving the fault, but distinction is not very high. So that means we need to really think very carefully, come up with the right result, interpret the results properly, and we will be learning that in our next lecture. Now let me summarize this lecture. We say we, as far as possible, we use existing literature data. Reason being, it helps us to model, it helps us to go with the programming, so we can do a simulation. It really gives a good results. And many times we believe in material test data and which are available, we may have some sort of difference, but we go ahead with the initial data, and then we go ahead with whatever the data collection. We should give a little more emphasis on the data quality and standardization, and slowly we'll learn about that, how do we go for the standardization of the data, particularly when we introduce a PCA. There's a one scheme to standardize it. Then what is the way forward? We say we have so many data. If it is possible, we go ahead with the fusion of the data. We try to interconnect in all the data. Are we able to come up with some correlation? There are material database, there is a number of packages, software packages. Now if I go ahead with the coefficient of friction or wear analysis something, there are a number of software where available, we can utilize it. But question comes, they are not really providing all the results. There are also some case studies, but question comes, are we really investigating only novel case studies or failure case studies also? So I'll give a little more emphasis also on the failure case studies, because failure case studies also teach us a lot. And then we give a little more emphasis on primary data collection to find out the better theoretical results or regression models, which we'll be learning in machine learning. One more thing which people also confuse is that they go with the individual tribo element analysis, as I say, gear pair. But gearbox has a number of elements. So we should go ahead with a system centric approach instead of individual type of elements label. Last one is that sometimes people say go ahead with a sensor driven perspective. Again, I feel that that is not correct. Sensors will keep giving some results. We require a knowledge perspective. So again, I don't go ahead with a complete sensor knowledge. We require sensor knowledge along with our domain knowledge, along with our expertization, so that overall fruitful results can be useful. So that's why I'm saying data focused perspective is inadequate, and we should not only believe on data. We need to use our domain knowledge, we need to use expertization, and then that's why it is important. If we believe only in data, results will not be very favorable to us. That requires little longer time to come up with a complete automation. However, how effectively we can utilize the data to minimize our work, that is more important. With this, I say thank you for attention. Thank you.